Our second learning target for this lesson is to introduce part 2 of the fundamental theorem of calculus and apply it to take the derivative of an integral. So the concept of part 2 is the relationship between derivatives and integrals based on the fact that they are inverse operations, much like multiplication and division, an exponential and a log function. When put together, they cancel each other out because they do exactly the opposite thing. So to demonstrate this idea, let's look at the following compositions of functions. So when we know we have a composition, we work from the inside out. So in the box, we are asked to take the derivative of x squared with respect to x. So I still have the integral of dx, but that derivative is 2x. So my second step is to now take the antiderivative or integral of 2x, which leads me back to x squared. So what we should see right away is that when we took a derivative and then followed by an integral, we ended up exactly with the same function that we started with. Let's make sure the same thing happens when we do the composition in the other order. So we'll start with the integral or antiderivative of 2x, which is x squared, followed by the step of taking the derivative with respect to x of x squared, which in fact does give us 2x. So we are left with the function that we started with. And I hope that both of those prove to you that when you combine an integral and a derivative, no matter which way you combine them, they will always cancel each other out as inverse operations. So here's a nice summary of what we just discovered. And that's basically what the part 2 of the fundamental theorem of calculus is saying. It just uses a lot more notation to get us there. So let's dissect what this is saying. If you have a continuous function f of x on a closed interval a to b, then its antiderivative, capital F of x, is defined by the integral or the antiderivative of f of x. And it is differentiable, meaning we can take the derivative of that expression. And when we do that, we get the derivative of this integral, which we just saw in that composition, so we know that some things are going to cancel out. And it's kind of a series of events that happens. So let's take it step by step. As soon as we see a derivative and an integral paired together, we can cancel those out. And I'm actually going to cancel that lower limit at the same time because a is a constant. And we learned in the first half of calculus that whenever you take the derivative of a constant, it always goes to 0. The upper limit, however, is a variable, so I know that derivative does not go to 0. I do want to mention that when we cancel out the integral, this dt, which is the variable of integration, goes away when the integral goes away. So after all these things have canceled and fallen away, we have left the upper limit, which is x, and it actually gets substituted in place of the t in that function f. So your final answer will be the function of x, which is your upper limit. So let's work through this first example and it'll give us a chance to practice those steps again. So the derivative and the integral, when put together, they will cancel each other. The constant of 4 gets canceled out as well because the derivative of a constant is 0. When the integral goes away, the dt goes away with it. So we're left with the upper limit of x, and that comes down and replaces your t. So your final answer will be 3x squared. The second example is pretty similar. The only difference is you have more than one place to plug in that x. So if you feel comfortable, go ahead and give that a try and check your answer on the key, and we'll talk about it in class as well. The next two, as you can see, have something other than x in the upper limit. So that's actually going to involve the chain rule. So what I'll do is skip this example because it's a little less scary, and we'll talk through this one. We start off the same way by canceling the derivative with the integral. That lower limit constant goes away, as well as the dt. And we still take our upper limit and replace the t with that. So we get 1 over sine x. The difference is that when we take the derivative of this integral, that upper limit has a chain rule derivative. And we know from the first half of calculus, we always have to multiply by our chain rule. So the derivative of sine x would be cosine x. And putting that together, the cosine would end up on top. So final answer would be cotangent. So if you'd like to go back to this one and give it a try, check your answer on the key. We'll definitely talk through this one in class as well because it has something going on with the order of the limits that we'll have to apply a property. And then we'll also save this application for class.